Welcome to EE698I Mixed Signal IC Design. This is lecture number 4. In the last class, we discussed about quantization and we looked at the two common assumptions that we make about this quantization noise or the quantization error. What were those? First, the quantization noise is treated as a random signal. And second, we assume that this quantization error has a uniform probability distribution. And this is distributed between minus delta by 2 to plus delta by 2, where delta is the step size of the quantizer. And if the allowed voltage values are from minus Vref to plus Vref, this step size is in turn equal to 2 Vref by 2 power n, right? Where n is the number of bits. We also saw that we can calculate the quantization noise power or the variance to be equal to delta square by 12, right? And from this we also saw that for a sinusoidal input, the maximum signal to quantization noise ratio, that is SQNR, is roughly 6n plus 1.76 dB. So in other words, if you know what is the SQNR, we can compute the number of bits to be SQNR minus 1.76 by 6 bits. Okay. Now let's see how to measure this SQNR in practice. Well, we need to measure this SQNR because in practice, this is how we will characterize the ADC to find how many bits the ADC can actually resolve the input. Okay, well, this because what I can do is I can take a 2-bit ADC, right? So it will have just 2 digital outputs. I can randomly add 8 lines and connect it randomly to ones and zeros, put it in a black box and tell you that this is a 10-bit ADC and sell it to you, right? So in this case, how will you find what is the actual number of bits that the ADC can resolve? So what we do is that we apply a sinusoidal input with the maximum amplitude and compute what is this SQNR, right? And from this we'll back calculate what is this n. Okay, and this n what we compute is called the effective number of bits, or simply abbreviated as ENOB, right? So this is ENOB, that is equal to this. Okay, so let's see how we can measure SQNR. So what we do, we take the ADC, give a sinusoidal input, right? So at the output, let's say we get some output waveform like this, right? This is a quantized sinusoid. Well, to find the SQNR, that is the signal to quantization noise ratio, we need to take the ratio of the signal power to the noise power, right? So essentially, we need to differentiate signal and the noise from this waveform. And it is clearly not very trivial to distinguish between the signal and the noise from this time domain sequence, right? So what do we do? Well, when time domain fails, we resort to the frequency domain, right? So in this class, first, we will briefly take a look at the frequency domain tools we use to analyze a signal in the frequency domain, okay? And a small disclaimer. So I'll skip all the mathematical rigor and show only the results and explain them in a qualitative manner to the extent a circuit designer needs to understand it, okay? And most of you might have learned it in more detail, in more depth in your earlier classes, right? So this will just be a quick brush up for you. As usual, in our case, we'll be dealing with both continuous and discrete time signals. So we'll be looking at both continuous time and discrete time frequency analysis, okay? Well, first, the ADC, what we do, we give a sinusoidal signal, right? So sinusoidal signal is what? It's a deterministic signal. That is, I can exactly know what is the signal value x of t for a given time, right? And to characterize such deterministic signals in frequency domain, what we use the Fourier transform. And if the signal is a continuous time signal, we use a continuous time Fourier transform. And for discrete time signals, we will use discrete time Fourier transform. And in practice, we use what is known as discrete Fourier transform. Right? So continuous time Fourier transform is computed using this equation, that is x of f is integral minus infinity to plus infinity x of t e power minus j 2 pi ft dt. Right? Similarly, the discrete time Fourier transform, which is x of e power j omega, which I'll also write it as x of omega, this is what summation n equal to minus infinity to plus infinity x of n e power minus j omega n dn. Well, what is dn? We are incrementing in steps of one sample, so dn is simply 1. Right? So I'll not show it. So one thing I want to highlight is that, or remind you is that, so let's say this is my f axis, this is the Fourier transform of a signal x of f. Say at some frequency f naught, the value here is a naught. Okay. So this does not mean that the continuous time signal x of t has a sinusoid at a frequency f naught with a strength a naught. Okay. So what this really means is that around f naught, we have a band of frequencies, right? And in a bandwidth of say 1 Hertz, the strength of this continuum of sinusoids, that is the combined strength of all the sinusoids, is a naught. Okay. So what is the strength at any given any given sinusoidal frequency? That is a naught by the total number of frequencies, that is infinite. So it's essentially 0, right? So this is similar to your probability distribution function, where the probability at any given point is 0, right? So essentially, you can think of this as a voltage or amplitude spectral density. It's like a density function. Right? We can also understand this by looking at the dimension of x of f, right? So if x of t is a voltage signal, it has units of volt, right? This has no dimensions. dt has a dimension of seconds. So this entire thing has a dimensions of volt second, or it's volts per hertz. Okay. So in a Fourier transform, only if we have impulses, right? Say f naught, f1, etc. So only if the Fourier transform has impulses, it means that the signal has the sinusoidal frequency. Okay. Well, in our ADC case, along with these deterministic signal, we also deal with random signal, right? And this random signal can be our quantization noise as well as random circuit noise. So what's the difference between a deterministic and a random signal? Well, if you take a deterministic signal, say a sinusoidal, and if we have a sinusoidal source, so every time I switch on and record the signal, we are going to get the same waveform, right? However, with a random signal, every time you measure, you get different time domain sequence, x of t, or discrete time sequence x of n. So which means if you take Fourier transform, each time you take Fourier transform of these signals, you'll get different values, right? So we cannot really work with that. So what we do is that in practice, we deal with a special kind of random signal called stationary random signals. Again, I'm using this word stationary in a very loose sense. So let's say for these stationary signals, although x of t and x of n keep changing every time we record the signal, what remains constant are the following. First is mean, which in most of the practical cases turn out to be 0. Okay. And second is what is known as the autocorrelation function. also abbreviated sometimes as ACF. Okay, so let's see what this autocorrelation function actually means. Well, so what it means is the following. So let's say we have a signal x of t. Say it's a random signal and say it's varying slowly like this. Okay. Well, let's say t equal to 0. I know I find the value so much. Say it's some x. So can I say anything about the value of the signal at a time, say t naught? Oops. Sorry. T. Okay. Well, if the signal is slowly varying, we know that value at x naught and value at t equal to 0 and t naught are going to be similar, right? So autocorrelation function essentially tries to capture this effect. So what it does is that, as the name suggests, it finds out how correlated the signal is with respect to itself, right? So what it says is that if we know the strength of the signal at a particular time, can we make some judgment about the signal at some other time instant? Okay. So how it is computed is as follows. Rxx of tau is, let us say we observe the signal for a duration of say t. So I'll do 1 by t, integrated over t, x of t plus tau, t tau. And in principle, we need to tend t to infinity, right? So we need to capture the signal for infinite time and then do this. So what we do here, we take the signal and we take a product of the signal with a shifted version of itself, right? And see what is the integral value. Okay. And discrete time, we have a similar definition. Rxx of m is, say we capture for n samples, summation over those n samples, x of n plus n. Again, we need to tend n to infinity to get the exact value. Okay. So if we take an autocorrelation function plot, right? Well, at tau equal to 0, what it is, we are essentially finding how the signal is related to itself, right? So we are taking x of t times x of t. So that's going to be the maximum, right? The signal will be related to itself, the maximum, right? And as we keep shifting the time, that is as tau varies, depending on how fast or how slowly the signal varies, even this autocorrelation will change accordingly, right? So if the signal is varying slowly, the autocorrelation will also do something like this. What it means? Well, there's a high relation or high correlation between the signal value at 0 and say at some other time instant, right? On the other hand, if the autocorrelation varies or dies more quickly, it means that signal also changes more rapidly, which means I cannot really say what is the signal value at another time instant given the value at some other time instant. Okay. And in the limiting case, you can have this kind of signals which has an autocorrelation function Rxx of tau equal to delta of tau. So what we have is a delta function at tau equal to 0. So what it means is that, well, there is absolutely no relation between any sample to any other sample. Okay. And in discrete time also we can have something similar. Rxx of n is a delta function. Okay. Well, in short, for random signals, what we saw, every time we record the actual time domain signal x of t or x of n, we'll get different values. But for stationary random signals, something remains constant, and what that is the autocorrelation functions Rxx of tau and Rxx of m in discrete time, right? So instead of taking the Fourier transform of these, it makes sense that we take Fourier transform of these signals, right, to get a frequency domain representation, because this is what remains constant for the signal. And if we take that, let's say I get these functions xx s xx of f, and discrete time I call it s of omega. Okay, so these functions are what are called as power spectral density functions, or sometimes or denoted as PSD. Okay, so what is the expression? It is integral Rxx minus infinity to plus infinity Rxx of tau e power minus j 2 pi f tau d tau, right? So similarly for the discrete time case, it is this summation m equal to minus infinity to plus infinity Rxx of m e power minus j omega n, right? Well, so as the name suggests, it's again a density function. So what it really gives is the power of a signal in a 1 Hertz bandwidth, right? So we can understand it if you look at the dimensions of this. So let's first look at what is the dimension of this autocorrelation function. Well, here I have, let's say if x is a voltage domain signal, so x of t has dimensions of volt. This also has dimensions of volt. This is second, and this has 1 over second, right? So overall, this has dimensions of volt square. Okay. So what is the dimension of this PSD, power spectral density? Autocorrelation has a dimension of volt square. This is dimensionless. This is second. So the overall dimension is volt square times second, or it is volt square per hertz. Okay. So just like how a Fourier transform gave the spectral density in terms of the amplitude, this is giving you the spectral density in terms of the power. Okay. So again, unless we have impulses at some frequency, if we have a continuous function like this at any frequency, say f0, if the PSD is looking like this, it doesn't mean that the signal has this particular sinusoidal frequency with this power, right? So only if the power spectral density has impulse at some frequency, it means that the signal has this particular sinusoidal frequency, and the power will be given by the strength of the impulse. Okay. Well, so if we take our this case where the signal was completely independent of its own adjacent samples. So if we have autocorrelation function of delta, what is the power spectral density? It is a Fourier transform, which is a flat, which is constant, right? So it's going to be a constant like this. This is frequency axis. This is the power spectral density. Similarly, in the discrete time case, so push it aside. If we had an autocorrelation function that is a discrete time delta, what we will get, again the power spectral density will be the Fourier transform of this, which is a constant. So we'll have the spectrum from minus pi to pi. It's a constant function. Okay. And these sequences or these signals which have an autocorrelation function of delta or a power spectral density which is a constant are called white noise sequence or white noise samples. Okay. And it is called white because if you look at the frequency domain representation, that is the power spectral density, they contain all the frequencies, just like how a white light comprises of all frequencies. Okay. And it turns out that this power spectral density is an even function, right? So let's say we take this white noise example. We have a function that is constant like this, right? So a power spectral density is an even function. So one way to qualitatively understand is that, well, for real signals, we need to have a sinusoid. We need to have both positive and negative frequencies with equal strengths, right? Only then we'll have a real signal. Else we'll end up with a complex signal, right? So that's why the power spectral density will also be an even signal. So instead of representing both positive and negative frequencies, so sometimes, or in practice, most of the times what we do is that we show only the positive range of frequencies because we know the PSD is an even function, right? So, and instead, let us say this value here is P0. We show only for the positive range of frequencies and say this is 2P0. Okay. We do the same thing for a discrete time case also. So let's say for a discrete time, we had something like this from minus pi to pi. So let's say it had some profile like this. Let me show something like this. What we do is that we show only the positive frequency range from 0 to pi, and we show this. And if this value is say P0, this we will represent as 2P. Okay. And sorry. So these this kind of PSD representation where we show both the positive and the negative frequency axis. So this is called a two-sided PSD. Right? Whereas this one where we show only the positive frequency axis is called one-sided PSD. Well, so let's now look at the expressions in some detail. So what we have Rxx of tau, that is autocorrelation function, which was limit t tending to infinity 1 by t integral over that time period x of t plus tau d tau, right? And we saw that if we take the Fourier transform of this autocorrelation function, we get the power spectral density, right? Well, so we can also write the power spectral, autocorrelation function Rxx of tau using the inverse Fourier transform, right? So how we can do? Well, I know the Fourier transform of this autocorrelation is the power spectral density. So I'll use the inverse Fourier transform formula to write this this autocorrelation in terms of the power spectral density. So Rxx of tau will be what? Minus infinity to plus infinity power spectral density times e power j 2 pi ft times df, right? So let's say we put tau to be 0 in this expression. What do we get? Oops. We get Rxx of 0, which is what? Limit t tends to infinity 1 by t integral over the time period x square of t dt, right? And what is this? This is simply the power of the signal, right? So what we have done, well, we can see that we can compute the power of the signal by computing the autocorrelation at 0 time shift. Okay. And from this expression, from the inverse Fourier transform expression, we can find that Rxx of 0 is what? We'll simply put tau to be 0. Sorry, this should have been e power j 2 pi f tau, right? We are looking at functions of tau. So here to get Rxx of 0, I'll put tau to be 0. So this becomes minus infinity to plus infinity is xx of f times e power j 2 pi f times tau. Since tau is 0, this becomes 1 times df. Okay. Well, so this power spectral density here is a two-sided power spectral density, right? So if I'm having only a one-sided power spectral density, I will simply write as integral 0 to infinity the two-sided power spectral density, which probably I'll call with a symbol tilde of f df, right? So similarly, in the discrete time case, we'll have something similar. So again, we can simply show following a similar procedure that Rxx of 0 simply but the power of the signal, right? And in a discrete time case, how can we find Rxx of n from the inverse Fourier transform? Well, the inverse Fourier transform is this 1 by 2 pi minus pi to pi s xx of omega e power j omega n d omega, right? So if you want to find the autocorrelation at zero shift, that is at n equal to 0. So what do we get of 0 is 1 by 2 pi integral minus pi to pi the power spectral density integrated over minus pi to pi. Again, this is a two-sided PSD. So if you have a single-sided PSD, so we'll simply have 0 to pi integral of the single-sided power spectral density. Okay. So what have we observed? Well, we can find the power of the signal by computing the power spectral density and integrating it over the entire frequency range. Right? For the continuous time, it is from 0 to infinity. For the discrete time, it is from 0 to pi. Okay. So let's try to make more sense of this result. So for that, well, let's take a simple signal. Say we have x of t as a naught cos 2 pi f naught t. So how will be the power spectral density of the signal? So let's say this is f axis and this is the power spectral density. Then we know this is a sinusoidal signal, so we'll have an impulse at the frequency f naught. And what will be the strength of the impulse? Well, this is a power spectral density. So this better be the power of the sinusoid, right? So let's say this is P naught, which is now A naught square by 2. Right? So well, the power of the signal is what? P naught. This is simply the strength of the impulse at the frequency f naught. Right? So let's say now we have one more signal, which is sum of two sinusoids. So let's say it is A naught cos 2 pi f naught t plus A1 cos 2 pi f1 times t. Okay, so how will the power spectral density of this look like? Well, it will have two impulses, right, at frequencies f0 and f1. Okay, and the impulse at f0, the strength of that impulse will be the power of the sinusoid, which is say p0, and here it will be p. Okay. Well, what is the total power of the signal? Well, we can easily compute, right, and this will be equal to sum of the powers of the individual sinusoids. Okay, I still suggest that you actually you take this signal x of t, okay, and compute the power of the signal and convince yourself that it is equal to the sum of the powers of this individual sinusoids. Okay, so now we saw we have two sinusoids. The power is equal to sum of these two, powers, right? And what are these? This is power spectral density value at these two frequencies. Okay. So now similarly, if we have, let's say, multiple sinusoids, okay, we'll have impulses at multiple frequencies in the power spectral density. So in this case, what will be the power? Well, it will be the sum of the power spectral density values at these frequencies, right? So let's say these are multiple frequencies, some f0, f1, f2, and so on. But I mean, so now instead of these impulses, let's say we have a continuum of frequencies, okay? Which means what will be the power now? It is going to be the summation is going to become integral, right? Because this is now a continuous function. So this will be the integral of the power spectral density from 0 to infinity. Right? Similarly, in the discrete time, we can similarly prove that this will be 1 by 2 pi integral from 0 to pi, the power spectral density is integral. Okay. Well, next let's see what happens when a random signal, say x of t, is getting filtered by an LTI system with a transfer function h of f. Okay. So let's say the output is y of t. Well, this could again be a discrete time sequence getting filtered by a discrete time filter with a transfer function h of omega, giving an output sequence y of n. Okay. Well, the goal here for me is to find what is the power at the output of this filter. This will always happen in circuits because we will have some circuit element that is generating noise, right? And that noise will be processed by some circuit, and we'll be interested in finding the noise power at the output of the circuit, right? So, well, we saw that to find the power, what we do, we take, let's say we want to find the power of y of t. What we do, we take the power spectral density of the signal SYY of f and integrate it from 0 to infinity, right? So now this simply boils down to finding the power spectral density of this output signal. So let's see how we can find it. Well, again, we'll resort to our simple and humble sinusoid. So let's say my signal x of t is a sinusoidal signal a cos 2 pi f naught t. Okay, and let's say that is going to this filter h of f. Okay, and the output is y of t. Well, we know that for x of t, which is a sinusoid at a frequency f naught, the power spectral density will be an impulse at that frequency f naught, and the strength will be the power of the signal, right? So when this filter goes through a filter, this signal goes through a filter h of f, what will be the output signal? Output will be again a sinusoid of the same frequency, right? Because this is a linear filter, not t. So what will be the amplitude? Let's say h of f has some response like this, right? So this is f, let's say this is magnitude of h of f. Let's say this is my frequency f naught. So what will happen to the magnitude? The magnitude of the sinusoid, that is a naught, that will get scaled by this value, right? So what will happen? At the output, the magnitude of the sinusoid will be the input amplitude, that is a naught, times mod h of f, right? So what will be the power spectral density at the output? Well, this is again a sinusoid. So we'll have an impulse at the same frequency f naught. Oops. And what will be the strength of the impulse? That will be the power of the signal. And what is this power? That will be the input power, that is P naught, times mod h of f square, right? Well, why? Because for this, the power is what? A naught square by 2. For this signal, what is the power? Because amplitude has been scaled by mod h of f, the power will be a naught square by 2 times mod h of f square, right? So what can we say from this? Well, my output power spectral density f is simply the input power spectral density times mod h of f square, right? Or for particular frequency f naught, I find that this is the case. So similarly, for any frequency, this will be the power spectral density, right? We'll have a similar expression for a discrete time case also. So the output power spectral density will be mod h of omega square, that is the magnitude square of the LTI filter's response, times the input power spectral density. Okay. So to summarize what we saw, well, we saw that for random signals, instead of computing the Fourier transform, we do what is known as the power spectral density calculation. And how do we compute the power spectral density? In theory, we find the autocorrelation function Rxx of tau, or in discrete time Rxx of m, and take the Fourier transform, right? And that gives our power spectral density. But in practice, instead of computing this autocorrelation function and computing its Fourier transform, there are other easier estimates to find the power spectral density. Well, what are they? Let's look at it now. The first estimate simply says that you can compute power spectral density approximately by computing the Fourier transform taking the magnitude square of it and then dividing it by the observation period t, right? That is the time period for which we have recorded the signal. In discrete time, we'll have similar, so 1 by n times mod x of omega square. And this estimate is called the periodogram estimate. Okay, this is not such a great, this doesn't give a very good estimation of PSD. So in general, what we resort to and what we will follow in this course as well is the Welch estimate. Welch estimate. And how do we do that? Well, let us say we are actually recording the signal for t in the earlier case, right? Or for n samples for the discrete time case. So what we do here is that we record it for a much longer time. So let's say we take it for 4 times t, right? So I'll have 4 segments, each with a interval of t, right? So this is t, 2t, 3t. Okay. So what we do is for each segment, we find the periodogram estimate. That is, we find the magnitude squared of x of f and divide it by the time t. Okay. We do that for all these 4 segments. Okay. So let's say this is giving some p1, this is giving p2, this is giving p3, and this is giving p4. Right? And in Welch estimate, what we do, we say that the power spectral density is approximately the average of all these p1 plus p2 plus p3 plus p4 by 4, right? So, or I can write it as an average of this periodogram estimate, that is 1 by t times the magnitude squared of the Fourier transform. Okay. So similarly for the discrete times, for the discrete time case, it will be average of 1 by n times magnitude of x of omega square, the discrete time Fourier transform. Okay. And to increase the number of segments you have for averaging, we can also do the following, right? And that's what we'll also do in practice. So this is my 4t as well. So this is t, 2t, and 3t. So what we do is that the first segment is from 0 to t. The second segment, instead of starting from, like just after t, we have an overlap. So we say that the second segment can start from somewhere here. Okay. So which means the third segment can start from here, fourth will come from here. And so we can have one more extra segment or few more, right? Depending on how many samples or how much time we allow this overlap for, right? So this way we can increase the number of segments available for averaging this mod Fourier transform square estimate. Okay. And in practice, we restrict the overlap to half the observation time or n by 2. Okay. Beyond that, the averaging does not yield any benefit. Okay. In short, what we do to find the power spectral density, in principle, we need to find the power spectral density by calculating the autocorrelation function and taking its Fourier transform, right? That's what gives us power spectral density. But we also saw that we can get a good estimate of this power spectral density by taking the magnitude squared of the Fourier transform, dividing it by t, and taking multiple averages of it. Okay. Well, this might seem a bit confusing because to start off, we said that for a random signal, each time we record the signal, we get different values. So if we take the Fourier transform, that will also be different each time, right? And that's why we came up with this autocorrelation function and power spectral density. And finally, it looks like we are taking the Fourier transform and using it, right? So but the point to be noted here is that it is true that each time you take the Fourier transform, we'll get different value, right? But it turns out that if you take multiple such Fourier transforms and average their magnitude squared, you get a very good estimate of power spectral density. Okay. So let's see some examples to understand. So what I've done here is that I've taken a random signal that has a white spectral density, that is a white noise sequence, so that it has a constant power spectral density, say somewhere here. Okay, and this is nothing but the periodogram estimate. That is, I have taken one segment and done this magnitude of Fourier transform square. Right, in discrete time, I have done this 1 by n times mod x of omega square. Right, and we can clearly see that there is a lot of wiggling. Right, there's a lot of uncertainty in the values. Okay, the next figure, the red portion, is one more periodogram estimate. That is, I've recorded the signal once again, right? And I've taken the mod squared Fourier transform, right? Again, we can see that there is a lot of variation between the first periodogram estimate and the second one, that is the blue one and the red one. Okay. So next, what I do is I take multiple such mod Fourier transform square estimate, that is mod x of omega square estimates, and then average. And I took around 50 such estimates and average them. And I find that finally I get this black curve, right? Okay. And this is more or less fairly constant. And as expected for a white noise sequence, I get a constant power spectral density, right? So this is another case where instead of taking a white noise, which has a constant power spectral density, I've taken a noise sequence which has a frequency shaping, right? If I zoom it, we can see, okay. So in this, the portion that is in light green, right? The light green curve, which I'm drawing on top like this, okay. That is the actual power spectral density of the signal, right? And the red one here is the mod square Fourier transform estimate, okay, for one segment. And as and the moment I took multiple such mod Fourier transform square estimates and averaged them, I get better results. So this yellow is with 10 averages, okay. And if I took some 50 segments and average it, I get the section that I get the curve that is shown in the violet color here. Okay. So okay, so one exercise for you is to think about how I would have generated this sequence. Okay. In MATLAB, I can easily generate a sequence which has a constant or a white power spectral density, right? A constant power spectral density. From this sequence, say if I call x of n, which has a constant power spectral density, I'll think of how I would have generated this kind of a frequency shaped power spectral density, or how would I have generated a sequence which has a this kind of a power spectral density. Okay. So well, let's get back to our quantization noise business, right? So in the last class, we saw that quantization noise, we assumed two things for the quantization noise, right? One, we assume that it's a random signal. Second, we assume that it has a uniform PDF, right? In practice, we make one more assumption, that is the quantization noise has a white spectrum or a white power spectral density. Okay? That is, we treat it as a white noise. Okay. So because of that, the power spectral density of the quantization noise, the single-sided power spectral density, if I call tilde, it will look like this. From 0 to pi, it's going to be constant, right? And of course, if I take 1 by 2 pi integral of this, that's going to be delta square by 12, right? Because we saw from today's discussion that this is essentially the noise power or the power of the signal. Okay. So with this understanding, let's get back to our earlier problem, that is how to measure the SQNR of the ADC, right? So what we do, we give a sinusoidal signal with a maximum amplitude to the ADC. At the output, we get a quantized signal, right? Something like this. So what we do, well, this signal contains both the signal and the quantization noise. So we treat it like a random signal and take the power spectral density. So how will the power spectral density look like? Well, this is, sorry, omega. This is the power spectral density, the single-sided power spectral density. Okay, from 0 to pi. So the quantization noise will have a flat power spectrum, so it will look like this. But I also have the input signal, which is a sinusoid, so I'll have an impulse as well at the input frequency. Okay, now to find the signal to quantization noise ratio, I need to find the signal power first, right? And what is the power of the signal? Well, we take the spectrum and look at the strength of the impulse, and that's going to give the signal power, right? Next, I need to find the quantization noise power, right? So how do I find it? Well, if I take the area of the entire power spectral density, what do I get? I'll get the quantization noise power plus the signal power, right? Because when we integrate the entire power spectral density, we'll also be integrating this impulse. So we'll get the sum of signal power and the quantization noise power. Since we already know the signal power, we can take the difference of this with this. That will give the quantization noise power. And then we can take the ratio of the signal to noise power, right? So this is how we can find the signal to quantization noise ratio. From that, we can find the effective number of bits as SQNR, that is what we measured, minus 1.76 by 6. So many bits. Okay. So in future, if someone cheats you by giving, a 2-bit ADC and then, like appending 8 random wires connected to ones and zeros, right? So you can take this black box, give a sinusoid, find SQNR like this, and then find the effective number of bits, right? And then you can truly know if the ADC can actually quantize the signal to 10 bits or 2 bits, 4 bits, whatever. Okay, let's stop at this point and continue from the next class.